Good evening. This is Mr. Lucy representing Mr. Sobolewski and Mr. Guevara, bringing you to our next e-learning cycle on acids, bases, and pH. And for links to the textbook, we're really doing page 467. This is really chapter 14, and I basically have highlighted what pages pertain to the specific areas that we're going to have you responsible for. And also, Mr. Sobolewski will also have a video on this topic on naming, and that will help tremendously. So let's get going. So the theory of acids and bases from Arrhenius is probably the one you're most familiar with. And for an Arrhenius acid, you basically have any substance, that has a hydrogen in it. I'm going to make that as AQ. And as the videos will tell you, we call this hydrochloric, and I underlined the key parts, hydrochloric acid. Some of you in my classes, we've already started the naming before we left, but I'm going to assume that no one knows the naming, and you'll basically go through the video and come up with questions for our Zoom meetings with Mr. Guevara, Mr. Sobolewski, and myself. So if I have something like H2SO4, that's a pretty common one. We call that sulfuric acid. And there's a little saying, little Willie studies chemistry, he studies it no more. What he drank for H2O was H2SO4. Now that's not to be confused with H2SAQ, which is hydrosulfuric acid. And you'll notice that when I have a binary acid, bi meaning just two, I have just two things here. I have hydrogens and sulfurs, I have hydrogens and chlorines. So the binary acids always have the prefix hydro and the suffix ic, and obviously acid at the end of it. It's that AQ, because if I said HCl, that's hydrogen chloride. It's only when I put HCl in a solution of water, I have hydrochloric acid. So the next major topic in acids and bases is this. This is always a topic that people miss a lot about concentration, which we've already done. For us, it'll basically be molarity. And without going into great detail, because we just finished this unit, it'll be molarity is equal to number of moles per liters. And everybody knows we can give you grams, and you need to be able to convert grams to moles. And we can also give you milliliters, and then the metric system kicks in. You need to be able to go through milliliters to liters. Strength is a little bit different than concentration. Strength is the ability to remove a hydrogen in a solution. And we'll talk more about that later. But for today, I want you to know that the concentration, when you see that in the textbook, it's the same concentration we've been doing in the past unit in our molarity unit. So let me turn the page here. And, oh, there we go. So as I'm back here, we start with Arrhenius. There's some problems with the Arrhenius definition of acids and bases. For Arrhenius, every acid contains a hydrogen, and every base contains an OH minus. So there is a base. So if I'm looking at NaOH, or if I'm looking at CaOH2, I know that they are both bases because I can clearly see I have the AQ and I have the hydroxide ion attached to some of the metals that I have, or even a 3-1 with my aluminum hydroxide. That would be also a base. So quick, easy definition, probably the ones you learned in 5th, 6th, 7th, 8th, and maybe even 9th grade. But as we get to chemistry, we find that there's some exceptions to the Arrhenius theory of acids and bases, and that leads us to the second theory, which we will spend a lot of time on this year, called the Bronsted-Lowry theory of acids and bases. Page 478 to 480 in your textbook. I urge you to give that a good read. And this was developed in 1923, less than 100 years old, and we're discussing it. So chemistry is evolving as we find new theories to replace past theories. That's how we evolve those concepts and make them more applicable, and also make them to where there's fewer exceptions as to why the theory doesn't work. So by now, prefixes of mono meaning 1, di meaning 2, tri meaning 3, and you can clearly see that this would be a mono, di, and a triprotic acid. Protic referring to proton, because if I look at the hydrogen, I have 1 electron, 1 proton, and 0 neutrons, although it looks like the word on. If I have a hydrogen with a +1 charge, I have no electrons, 1 proton, and no neutrons. So we basically call their 3 dots mean therefore. So therefore an H+ ion is the same thing as a proton. So our basic template is, for Bronsted-Lowry that is, I'm looking for an acid and a base. So my acid, my base will yield a conjugate acid and a conjugate base. We'll talk about those terms in a second. Notice the arrows go both ways. So as the reaction is going this way, these are combining and it's going back, and then it's going back, and then it's going back. There's a huge area of this in AP Chem, which I won't get into now. And Bronsted-Lowry, instead of saying an acid contains a hydrogen, instead of saying a base contains OH, we're just dealing with that H. So an acid will always have 1 more hydrogen than its conjugate base. Let me say that again. An acid will always have 1 more hydrogen than its conjugate base. So this must be my acid. Here's my conjugate base. And this must be my base. Here's my conjugate acid. So let's see if that application, if that definition applies. My acid will always have 1 more hydrogen than my base. Now, I want to spend a couple seconds here. On each side of the double arrows, I have 1 acid and 1 base. 1 acid and 1 base. Clearly, the commutative property of addition can apply here, and these two can be flipped, or these two can be flipped. But you will never have an acid and an acid, or a base and a base, or a conjugate acid and a conjugate acid, or a conjugate base and a conjugate base, or an acid and a base here. So this setup is pretty foolproof. And the next thing I've noticed over the years is just count up the hydrogens. I have 5 hydrogens. I have 5 hydrogens. All I'm doing is shifting a hydrogen from my acid to the base, because our definition of a base is it'll accept the proton, it'll accept the hydrogen. So when my base accepts a hydrogen, H2O becomes H3O plus, and now that becomes my acid, because my definition of an acid is it can donate a hydrogen. So my H3O plus loses a hydrogen, that becomes H2O. So you can see where this goes back and forth. It's a base because it takes a hydrogen. When it takes a hydrogen, it turns into an acid. It's an acid because it donates the hydrogen. When it donates the hydrogen, it turns into a base where it can accept the hydrogen and turn into the acid, and back and forth and back and forth, which is why there's only 1 acid and 1 base on either side. So I think the salient point here is this. I have 5 hydrogens. I have 5 hydrogens. All I'm doing is making my acid donate a hydrogen. And when H3PO4 donates a hydrogen, it turns into H2PO4, a base. And my base, H2O, can accept the hydrogen. And when it does, it turns into H3O plus, which is an acid. So let's follow this down. So in this case here, I'm looking at my H2O and my H3O. Which one has more hydrogens? This one does. So that's my conjugate acid. Therefore, that's my base. And like we said, I can't have 2 bases on one side. So that must be my acid. That must be my conjugate base. So come over here. I have HPO4 2 minus and PO4. Which one has more hydrogens? This one does. So that's my acid. This is my base. Notice there's no OH here. There's not even a hydrogen there. So my Arrhenius theory does not apply with OH for being a base, nor I have a hydrogen there at all for making an acid. And so between these two, this has to be my conjugate acid, and that has to be my base. So look at this. I have one substance, HPO4 2 minus, which is technically a base, and I have HPO4 2 minus, which is an acid. I have H2PO4 minus, which is a base, and I have H2PO4 minus, which is an acid. So you can see the power of the Bronsted-Lowry theory of acids and bases. It depends on what that acid is met up against with and what the products are after they react, which confirms whether it's going to be a conjugate acid or a conjugate base. And let's turn the page. So for Arrhenius, acids are just hydrogen containing and bases are just OH containing. For Bronsted-Lowry, well, we don't look at the OH, we look at the donation and acceptance of an H+, which is also a proton. So we call them monoprotic, diprotic, triprotic, or multiprotic acids. And for Lewis, that's the newer theory of acids and bases, which we have to wait till college because I think we have our hands full with these two here, mostly with the Bronsted-Lowry. So this shows the march of science. For the longest time, our definitions of acids and bases with Arrhenius, H+ acids, OH- base was just fine. until we found some exceptions. And then a new theory came along that has fewer exceptions. So then we stuck with the Bronsted-Lowry. And roughly, the exceptions in Bronsted-Lowry can be explained with the Lewis acids and bases theory. So that's a nice little schematic or timeline as to how we do this. So 3 practice problems, and then we'll be done. And here's the term that I purposely did not use on my previous slide. Let's see if it even applies here. So HF and F, these two look like they go together. These two look like they go together. This one has one more hydrogen, so that must be my conjugate acid. That must be my base. Therefore, that must be my acid. That must be my conjugate base. And if I look at these here, look at this, NH3 and NH4. Wow, that has one more hydrogen. That must be my conjugate acid. There's my conjugate base. And, oh, whoops, I goofed there. Let me just erase that. There's my base. And over here, that must be my acid. And this must be my conjugate base. Notice one more hydrogen, one less hydrogen. Notice one less hydrogen, one more hydrogen. And as I'm over here, H2SO4, I'm going to look at these two. This has one more hydrogen, so that's my conjugate acid. This is going to be my base. And so this has one more hydrogen. So there's my acid, there's my conjugate base. And if I did this right, and I'm 100% sure I did, I see in one case, water's the acid, in another case, water's the base. And I think that's what we're applying to that concept right there. And there's a little bit of trivia here for you. This is the main reason why we've abandoned the Arrhenius, because this is a base, but according to Arrhenius, right, it doesn't contain the OH minus. So this is one of those exceptions that led us to the advancement to the Bronsted-Lowry theory in the early 1900s and less than 100 years old. So I know I went fast. Know this term, amphoteric, on page 485. It's when a substance can act as an acid or a base, depending on which situation it's in. And notice I have it here. I'll put a little green star here, here. I have it here, and I have it here. And you might note that I have a polyatomic ion with fewer hydrogens, so I have a charge. And whenever I have that type of situation, I'll always have something that's amphoteric. In one case, it's a base. Over here, it's an acid. In one case, it's an acid. Over here, it's a base. So hopefully, I didn't go too fast for you, but you can always rewind the video. And in essence, thank you. And I appreciate your time. And I don't know what I just did with the screen, but I will go back and end the video.